Hey there, and welcome. Today, we're going to be detectives in a chemistry lab. We've got a really colorful mystery on our hands, and believe it or not, our number one clue is going to be light itself. We're about to see how light can help us measure something that, to our eyes, is completely invisible. So here's our puzzle. We've got these three solutions, right? They all have the same blue dye in them. And just by looking, you can tell some are, well, they just look more blue than others. But in science, just saying something looks like it's darker doesn't really cut it. We need a number. We have to know exactly how much dye is in each sample. So the big question is, how on earth do you turn a color into a precise measurement? Well, the key to cracking this whole case comes down to a really important principle in both chemistry and physics. You can think of it as our secret weapon, the thing that lets us turn a simple observation about color into a hard, concrete number. It's called Beer's Law. So, what is Beer's Law? At its heart, it's a really simple idea. There's a straight line relationship between how concentrated a solution is and how much light it soaks up. It makes sense, right? The more dye you have, the more light gets blocked. This whole relationship is wrapped up in one neat little formula, A equals epsilon times L times C. To really get it, we need to break down what each of those letters means. Okay, let's start with A for absorbance. Just imagine you're shining a flashlight through a glass of blue Gatorade. Some of that light is going to get trapped or absorbed by those blue dye molecules. The darker the blue, the more light gets trapped. Absorbance is just a number that tells us how much of that light didn't manage to make it through to the other side. Next up, we've got that funky-looking epsilon, the Greek letter epsilon. This stands for molar absorptivity. Now this is cool. Every colored chemical has its own unique ability to absorb light. You can think of it like a chemical fingerprint. For our specific blue dye, this value is a known constant. It's a key piece of the puzzle that we already have. Then we have L for path length. This one's super straightforward. It's just the distance the light has to travel through our solution. In the lab, we use these special little containers called cuvettes, and they are manufactured to have a standard width of exactly 1 centimeter. That means for our whole investigation, the path length is also a constant, which makes our lives a lot easier. And that brings us to the final piece, C, concentration. This right here is the big one. This is the mystery we're trying to solve. It's the exact amount of blue dye dissolved in each of our mystery solutions, and it's the answer we've been looking for. So, we have our law. But before we can just go and use it on our mystery samples, we need to calibrate our tools. It's kind of like making sure your bathroom scale is set to 0 before you weigh yourself. We need to build what I like to call a color ruler, basically a reference chart that connects concentrations we already know to the absorbance values they give us. And the way we do that is with a process called serial dilution. We start with a solution where we know the concentration perfectly. We measure its absorbance. Then we take out exactly half of it and replace that volume with pure water. What does that do? It cuts the concentration perfectly in half. We measure the absorbance again, and then we repeat this whole process over and over, creating a whole series of standards, from dark blue all the way to very light blue. Now, you might be asking, why do all this diluting? Well, it turns out Beer's law works best in a specific range. It has a sweet spot. If a solution gets too dark and too concentrated, that nice, neat, linear relationship we're counting on starts to break down. So our goal here is to create a whole set of data points that are all playing by the rules, all within this reliable, linear region. That's what gives us a clean, accurate tool. All right, all the prep work is done. We have our data from our known solutions. Now it's time for the really cool part, seeing how this data builds the master tool that's going to crack this case wide open. If you look at the data in a table, the relationship is just staring you in the face. As the molarity, that's our concentration, goes down with each dilution we made, the absorbance we measured also goes down. It's a perfect direct connection. But honestly, a table is one thing. Seeing this data visually is where the magic really happens. So we take that data and we make a simple graph, an XY scatter plot. We put our known concentrations along the bottom, on the x-axis, and we put the absorbance we measured for each one up the side, on the y-axis. Each one of our known solutions now becomes a single dot on this graph. And here it is, the crucial moment. When we plot those dots, they form a beautiful, nearly perfect straight line. And any straight line can be described by an equation. In this case, y equals m times x. This is it. This is our ultimate decoder ring. It's the mathematical summary of our color ruler. Our absorbance is the y, our concentration is the x, and that m value is the exact relationship that connects them. And you see this number here, the r squared value? You can think of that as our confidence score. A perfect 1.0 would mean our data points form a flawless, perfect line. Getting a 0.998, that's incredibly close. It tells us our color ruler is extremely accurate and super reliable. We've built a fantastic tool. The moment of truth is finally here. We've built our tool, we've calibrated it, and we know it works. Now it is time to take our 3 mystery samples and finally reveal their secrets. And because of all that prep work, the process now is unbelievably simple. For each unknown solution, all we have to do is put it in the machine and measure its absorbance. That number is our Y value. We just plug that number into our trendline equation and solve for X. And boom, just like that, the mystery concentration is revealed. And here is the big payoff. Remember way back at the beginning, our visual guess? We might have said, yeah, unknown 2 definitely looks the bluest, the darkest. Well, now science can actually confirm that. But here's the difference. We've gone from a gut feeling to a precise, calculated result. We have replaced "I think so" with "I know so." We've swapped ambiguity for certainty. So what's the big takeaway from all this? We started with a simple question about color, and we ended with a really powerful scientific tool. By understanding Beer's law, that simple relationship between light and matter, we built a graph that lets us measure the amount of a substance with incredible accuracy. We've literally made the invisible visible. And this all leads to one last really fascinating question. We use this technique, it's called spectrophotometry, to measure a simple blue dye. But think about what else this could be used for. Scientists use this for everything, from analyzing the amount of iron in your blood to checking for pollutants in a water sample. This basic method of using light to see the unseen is one of the most powerful tools in all of modern science. So you have to wonder, what else can it help us see?